We are going to do an example with a lot of groups, partly just to show that it doesn't matter how many groups there are. There's a system, you follow it, and you can get your hypothesis test. My kids are interested in playing Among Us. I'm not super clear on the rules yet, but you have people who are different colors playing some game, and we're going to record how long you survive based on the color. There's apparently some theories that certain colors don't last as long. Some of them can last 40 days. Red is the smallest. See, I made up this data. I should have thought about what shirt I was wearing, and now suddenly I regret it. But we're already recording, and our standard deviations, these are big. You can have standard deviations larger than X bar if you have skewed distributions and if you're making up data. So let's roll with this. Now, my first question is going to be, can I do this? And it never said assume normality. And do all my sample sizes have more than 30 data points? Well, no. Green is the one that's making it, so I can't do this.
You think you can do these things, but you just can't!
So I'm going to fix that by changing the 15 to be a 45. Now that's good enough. Also, I want to add assume equal variances. Now those are the assumptions for ANOVA. We're okay to do this. First thing I want is an overall average. I don't have the overall average. I have averages for each of the group. But if I take n times x bar here, that'll tell me the total sum for the orange shirted people. And then for yellow and on down, then divide by the total, which I added up all the n's and got 438. There is my overall average, 35 minutes. So if you're playing Among Us, you should live 35 minutes. Is that real? I don't know. I made these numbers up. I haven't played the game. But we do have some values that we can already put in our ANOVA table. We know that we have 6 groups. And is it supposed to be groups or is it supposed to be regression? I just ended up calling it model because I was tired of switching it back and forth between groups regression. The name here doesn't matter. So I'm going to put 5 here. That's 6 minus 1. 438, so 437, which is n minus 1. And then the 438 minus 6 gives me 432. Quick check. 5 plus 432 does equal 437. Oh, good. Let's go back here. What do I want next? I want to find the SSG piece, in regression called SSR. If you don't want to worry about it, we'll just call it SSM for model. And what do? I'm going to take n times this x bar, subtract the overall x bar squared, which gives me about 6,000. Then I'm going to take 102 times quantity 30 minus the 35 squared, gives me on down for each of these. And yeah, I'm pausing the video, but really each one of these took me 20 seconds to figure out. So a minute or two, you can kick out all of these. And then for the SSE, I'm going to be taking n minus 1, which is 59, times s squared, which is 54 squared. 59 times 54 squared gives me about 172,000. And see, you might have thought these SSM pieces were huge because they're in the thousands, but it's relative. The SSE is also in the thousands. So we need to work it all the way out to see how the test is going to end. And yeah, I paused the video again, but 20 seconds each, so 2 minutes here, 2 minutes here. It takes about 5 minutes to get to where we finally add up the SSM and the SSE pieces to get the totals for SSM and SSE. And you're thinking 30,000 for SSM and 1.3 million for the SSE. Those means are not very spread apart, but hold on, because this came from a whole lot of data, whereas this was only looking at 6 means. That's why we need to put this in the ANOVA table so that we can put those values next to the degrees of freedom. That way when we take this divided by the degrees of freedom, our mean square error come out fairly balanced. 6,000 versus 3,000 leaves us an F value of about 2. We're now ready to do our hypothesis test. We want to begin with the null hypothesis, and we can do it in symbols, sure, but turns out it's too long to really fit. Plus, when we get to the alternative, we don't want to use symbols. Maybe mu1 and 2 are equal, but mu3 and 4 equal to each other, but are different from those. Maybe mu5 is the only one that's different. Maybe mu1 equals mu6, but not any.
You see much, Aylmer, son of ailment. Too much.
Nah. So let's just write it with word. The null saying color is not related to average life. The alternative, how long you live depends on color, which is what my kids say. It's always blue. I don't know what that means, but the point is, color is not related. Some students think is not means not equals. That statement should be in the alternative. No, no, no. Color is not related to average life means that the life expectancy doesn't change as you move across the colors. That's an actual equal statement hidden in there. So be careful with the language and the wording. I know my alpha and F. In this case, I couldn't take the square root of the F to get a t-score. That only works when there's a 1 right here, which is true if we have two groups or if we're talking regression. But the idea is still the same. Now I can go to the application. F distribution, degrees of freedom for model are 5, degrees of freedom for error were 432, and then my t-score was 2.117. F distribution is always right-tailed because that's both the negative and positive side of the F. I mean, when you squared it, it folded over on itself. So this is a two-tailed test by only using the right tail. P-value 0.06240. I don't need to double that p-value because when I squared things, the negative and positive both got doubled. So there's my p-value. Failed to reject. What kind of conclusions can we make? We could not show the alternatives. So you could say we can't show color relates to how long you live on average. Our data doesn't say the average life differs across the colors. What am I probably going to say, my kids? Shirt color doesn't seem to affect how long you live. At least our data didn't show that. So doesn't matter what color you pick, just don't be an imposter, whatever that means.